In this last part of the talk, we are in position to give a brief sketch of the proof of our non-existence main result. So remember that we are considering singular spheres with a metric Hj that put a conical singularity of codimension 2 along a grid circle of codimension 2. So when A is larger than 1, we have seen that the Yamabe constant of the whole singular sphere is equal to its local Yamabe constant, so we cannot apply the existence result of Akutagawa, Kazuo, and Matsuo. And these two quantities are equal to the Yamabe constant of this sphere. We have also seen that the Yamabe functional computed on HA is strictly bigger than the Yamabe constant of the sphere. So even if J is Einstein, it is not a Yamabe metric. It is not minimizing. So when A is larger or equal than 2, with Kazuo Akutagawa, we showed that the conformal class of the metric HA does not contain any Yamabe metric minimizing the Yamabe functional. So as we said before, the proof is by contradiction. We start by assuming that a Yamabe minimizer, so a Yamabe metric, does exist in the singular spheres. And then A is bigger than 2, we consider B as A over 2. So this is larger than 1. And we have a double branch cover of the singular sphere with the metric HA, so angle 2 pi A along a two-dimensional grid circle, and the sphere with the metric HB, so angle 2 pi B over along a codimension 2 grid circle. So this is a two double branch cover. And we get inspiration from the following lemma, which is due to Aubin in the case of normal coverings and to Kazuo Akutagawa and Andan Neves in the general setting of any covering. If you consider a compact smooth manifold of dimension larger than 3 with positive Yamabe constant, then a finite covering of this manifold of order k bigger than 1 has a strictly bigger Yamabe constant than the one of the manifold. Okay, so the idea is to try and show the same in our setting of singular spheres, so that if we can prove an analogous of this lemma, we get that the Yamabe constant of the sphere with the metric HA is strictly bigger than the one with the metric HB. But remember, A is larger than 2, so B is larger than 1, 2, and both A and B are larger than 1, so we know that those two constants are both equal to the Yamabe constant of the sphere. So we get an absurd, because if a Yamabe minimizer exists, we get a straight inequality between two quantities that are actually equal. So we would like to do something like this. We want to prove that the Yamabe constant of the singular sphere with the metric Aj is strictly bigger than the one with the metric Hb. So the goal is to assume that there is a Yamabe minimizer on Sn with the metric Aj and construct a function on Sn with the metric Hb such that the Yamabe functional of Hb computed on this test function V0 is strictly less than Yn, the Yamabe constant of the sphere, which happens to be the Yamabe constant of the singular sphere with metric Aj. Okay, let's do that. For a point in Sn, we consider its two fibers with the covering P2, and we define for the Yamabe minimizer U the function V as the sum of ux1 and ux2 for any x in the sphere. And then this similar function in which instead of taking ux1, we take ux1 to the power q, okay? Then consider the conformal Laplacian associated to the metric Aj. And since the Yamabe minimizer U satisfies an equation on the regular set of the singular sphere, we also have an equation for the function V, which is going to be used in the following. So it is given by this. If you compute the conformal Laplacian on V, you find something in which you have the Yamabe constant of the sphere and this function V to the power, this function VQ, where Q is this quantity, depending on the dimension. And this equation is true only on the regular set of the singular sphere, because the Yamabe minimizer only solved the Yamabe equation on the regular set. Now, consider V0 on the sphere with the metric HB, such that V is the lift of V0 on Sn with the metric AJ. And now we want to compute, this is the test function that we need in order to show that this function is strictly less than the Yamabe constant of the sphere. So let's compute the Yamabe function on V0, and this will be something that depends on V, its lift, and here you have a factor that depends on the order of the covering, which is just 2. Here, imagine that we are just on a smooth sphere. Then if the sphere was smooth, we would just integrate by parts, and integrating by parts gives you the conformal Laplacian of V times V. And then using the equation that it is satisfied by V, you will get something that makes the Yamabe constant of the sphere come out, and a product between V and VQ. And then when you're here, you just need to use, in a wise way, Hölder's inequality, and you get the strict inequality with the Yamabe constant of the sphere. So remember that we are on a singular sphere and that V satisfies an equation with the conformal Laplacian only on the regular set. So this step is not that easy because you need to be allowed to integrate by parts. And remember that for a Yamabe minimizer, the gradient can explode close to the singular set. It is since the angle are larger than 2 pi. And this part is just using Hölder's inequality twice. So if we are able to do this first step, integrating by parts, then we are done. So let's see why we can do this integration by parts. The idea is that you can write this term in this way. You take away from Sn a tubular neighborhood of its singular set, and you make the size of the tubular neighborhood go to 0. Away from the tubular neighborhood of the singular set, you are on a smooth manifold. So you integrate by parts, you get the conformal Laplacian as you want, but then you have a boundary term here that involves V and its gradient. So in order to get an integration by parts, you need this boundary term to go to 0. In order to do that, you use the regularity results that I've stated before for Yamabe minimizers. In particular, you know that V has exactly the same regularity as the Yamabe minimizer, so it is Sobolev bounded, so you don't care about this V here because it will be just bounded. And moreover, you know that it is Hölder regular with an exponent which is strictly less than 1, given by 1 over A. And you know something more about the behavior of the gradient of this function V close to a tubular neighborhood, away from a tubular neighborhood of the singular set. So here you have something that goes to infinity when the distance to the singular set goes to 0. Why this is still enough in order to get that this boundary term goes to 0? It's because you need to remember that the singularities have codimension 2, and this helps when estimating this term. Indeed, you can estimate this by the infinity norm of V times the volume of the boundary of the tubular neighborhood of the singular set, and times the epsilon to the power nu minus 1. So this is the size of the tubular neighborhood. And now, since the singularities have codimension 2, the volume of this boundary of the tubular neighborhood actually goes like epsilon to the power 1. So you get rid of this minus 1, and since nu is positive, you just get a constant time epsilon to the power nu, 1 over A, and this goes to 0. So when the size of the tubular neighborhood goes to 0, you get that this boundary term also goes to 0, and you can get the integration by parts. So you finally find that the Yamabe functional computed on the test function V0 is strictly less than the Yamabe constant of the sphere. So you get that the infimum of this functional, so the Yamabe constant of the sphere with the metric HB, is strictly less than the Yamabe constant of the sphere, which was the Yamabe constant of the singular sphere with metric AJ. But we know that B is bigger than 1. So both these quantities are equal, and they're equal to the Yamabe constant of the sphere. So there's an absurd. And if a Yamabe minimizer does exist, you get to a contradiction. So a Yamabe minimizer on a metric Sn AJ for a bigger than 2, cannot exist. And the proof of non-existence is done. Now, it is easily seen why this argument doesn't work for a between 1 and 2, because you do not get to a contradiction when you use the covering arguments. Indeed, if a is less than 2, the quantity b, a over 2, is strictly less than 1. And so the Yamabe constant of the singular sphere, the metric HB, is actually strictly less than the Yamabe constant of the sphere. So you don't get any contradiction with this kind of argument. One might think that maybe by following Viaclovsky's proof, the one for the isolated conical singularity, one can get somewhere. But there is a problem, which is again related to the regularity of the Yamabe minimizer. Indeed, the proof of Viaclovsky relies on an Obata type result. And for this, I mean the following. It is known that on a compact smooth manifold with an Einstein metric, whenever you have another metric in the conformal class with constant scalar curvature, this conformal metric needs to be Einstein as well. And remember that the example of Viaclovsky, the four manifold, the four orbifold, had an Einstein metric Gn, and Viaclovsky was able to show something similar to the Obata type result. So if you pick a conformal metric, a Yamabe metric in the conformal class of Gn, so a metric with constant scalar curvature, this conformal metric needs to be Einstein. And starting from that, he was able to get to a contradiction. But in order to get this first step, that a conformal metric with constant scalar curvature is also Einstein, he used that the Yamabe minimizer, the Yamabe, the conformal factor of the Yamabe metric is Lipschitz in his case. And for us, this is not possible because the Yamabe minimizer, in the case of singular spheres with angle larger than 1, angle larger than 2 pi, is never Lipschitz. The older regularity that I presented before is sharp. So you cannot prove this kind of result. So the case of a between 1 and 2 is more difficult than the one with a bigger than 2. Now, before skipping to some consequences of these non-existence results, I would like to spend some few minutes about the case of a less than 1 in order to show you what you can do when the Yamabe minimizer is Lipschitz. So one way of formulating Obata's result is the following in the case of smooth on a smooth sphere. If you consider the round sphere, smooth without singularities, of dimension larger than 3, you have the following result if there is a conformal metric. Whenever you have a conformal metric in the conformal class of the round metric, which has constant scalar curvature, then this metric is obtained from the round metric by a conformal diffeomorphism. So you have infinitely many metrics with the Yamabe metrics, all conformal to all obtained by conformal diffeomorphism, so as a pullback of a conformal diffeomorphism from the round metric. And this is actually true also in the case of spheres with a conical singularities of codimension 2 and of angle less than 2 pi. More precisely, we prove the following. If you have a singular sphere of dimension larger than 3 and the parameter is less than 1, so angle less than 2 pi. Then the metric AJ, as we said, is a Yamabe metric. And moreover, if I find another metric and its conformal class with constant scalar curvature, then this is also Einstein, and it is obtained from AJ by a conformal diffeomorphism that preserves the singular set. So this relies on a rigidity theorem for stratified spaces of with angles less than 2 pi along the codimension 2 stratum, and first eigenvalue of the Laplacian equal to n, and this is the case for those singular spheres. And it also uses a lot the Lipschitz regularity of the Yamabe minimizer. So with this in hand and the non-existence result, we are able to state something about the singular Rn we started from at the very beginning of the talk. So with the computation of the Yamabe constant of the singular Rn, you get optimal inequalities, Sobolev inequalities on the singular Rn. So remember, Rn was endowed with a metric GA, which is a product of the Euclidean metric on Rn minus 2 and a conical metric. So when A is, sorry, this is less or equal than 1. When A is less or equal than 1, you have an optimal Sobolev inequality where here the constant is given by the Yamabe constant of the singular Rn. And moreover, thanks to the previous result, you know all extremal functions for this Sobolev inequality. Extremal functions meaning functions that attain the equality in this inequality. They're all obtained from this function that we introduced before by dilations and translation. Dilations and translations are the conformal transformation that preserve the singular setting, the singular set. But when A is bigger than 1, then you have another optimal Sobolev inequality with this Yamabe constant of the sphere appearing here. And if A is larger than 2, there are no positive extremal functions for this inequality. Okay, so we'll finish with some open question. The first one is, of course, how could you get non-existence for A between 1 and 2? Because remember, the metric HA is an Einstein metric, but it is not Yamabe. So the guess is that even between 1 and 2, there should not be any Yamabe metric. Then if you pick a sequence of metrics that are minimizing, meaning that the Yamabe functional computed on the conformal factor converges to the Yamabe constant of the sphere, meaning the Yamabe constant of the singular sphere. What happens to this kind of sequence? What can we say to the limit of those conformal metrics? And then for the Sobolev inequality above, there are no extremal functions when A is bigger than 2, positive, but can one find changing sign extremal function? This is a more analytic question. And more generally, more long-term questions are related to the Yamabe problem on stratified spaces. So we have seen a non-existence result, but there are also positive things. There is some existence. In particular, if you consider a compact stratified space with just codimension 2 singularities with angle larger than 2 pi. If the dimension is larger than 6 and the metric is not locally conformally flat, then you can use an argument by Thierry Aubin in order to find a test function that shows that the global Yamabe constant of this compact singular manifold is strictly smaller than the Yamabe constant of the sphere. And remember, the Yamabe constant of the sphere in this case is exactly equal to the local Yamabe constant. So here you have strict inequality between the global and local Yamabe constant, so you can apply the existence result, and you get that a Yamabe metric does exist. So of course, the question is to study what happens in the case of equality. And remember that Schoen used, in order to study the case of equality, he used the positive mass theorem that he proved with Yao. So one possibility, which is a long-term project, is try and understand whether a positive mass theorem can hold in this kind of setting, meaning that you consider a compact smooth manifold with codimension 2 singularity of angle larger than 2 pi. You make an explosion of this compact manifold and you get an almost locally Euclidean, asymptotically locally Euclidean open manifold with a compact singular set. And can you do a positive mass theorem in this kind of singular manifolds with angles that are larger than 2 pi? And then can one show a rigidity statement when you have equality between the global Yamabe constant and the local Yamabe constant? And in this case, the rigidity statement that we hope would be that the manifold is actually conformally equivalent to our singular spheres. And in that case, we would get more examples of non-existence. And this is all I wanted to tell you in this talk. Thank you very much for your attention and feel free to ask questions.